Thank you very much for the introduction with so many details. And as my colleague Christian said, I'm from AIT, and I will show 2D monitoring solutions which we are doing in 2 different projects, about which I will say something more at the end of my presentation. At the beginning, I want to introduce you also the AIT, Austrian Institute of Technology, which is Austrian largest RTO organization in Austria, and we are providing applied science to the industry. We have 6 different divisions and also some laboratories in Seibersdorf. We are located in Vienna, and in our high-performance vision systems competence unit, we are focusing on high-speed sensing, which demonstrates, as you can see here. We have also initially computational imaging, so a method for creating a 3D scan of different objects. So we have 2 demonstrators here for that. And also we are providing some solutions for AI-based inspection. And going back to my presentation and to the main topic, I would like to focus on 2 different solutions for 2 different scenarios. First one is wire arc additive manufacturing, so WAM. This is a very hot topic now because it can produce very big parts. It can also produce like in a regular 3D printer with powder, but with the wire which is fed to the torch, and we are using the welding technique to just put layer on a layer in order to produce even very big objects. So we are using heat to just melt the wire and then to put everything together layer by layer to provide, for example, okay, just 1 second. Okay, now we should have laser point. So we can provide and build very big objects and with very difficult structure, for example, for other methods. And also, this method is very interesting because we are reducing the waste, and we can reuse even the material later. So, for example, for titanium welding and using titanium for building these objects, it's very important because titanium is very expensive. We are also focused on reducing the waste and also increase the efficiency of the production, so this is very important now. And yes, the other scenario is structural gas metal arc welding, so more traditional welding method, but also with 2 different modes. In the other project, we are using pulse multi-control method and Fronius cold metal transfer. So as you can see, our partner is Fronius. So this is one of producer of different solutions for the welding. And they are also producing cameras. Yes, and this PMC method is used to melt the wire and to melt this wire to join different 2 parts in very high speed and also with very high accuracy, which is also very economical because we are reducing the possibility to make some faults during welding. We are reducing the time which is needed for example, re-welding everything from scratch again or repairing the weld. So this is very important now also. And in this method, we are using pulses. So the arc and the current is like in sinusoid, going from higher value to lower value. So every time there is some current used, so the arc is always visible. And the other method is used for cold metal transfer. So we are using the heat and the arc for a very short time just to melt the wire, and the wire is put on the surface between 2 different parts without very big heat transfer, like in, for example, PMC method. So this method is very useful, for example, for materials which can be distorted by the heat or which are very thin, like, for example, aluminum rolls or something like this. So this is also a very interesting method. And in this method, we are using arc for a very short time. So this is very important for later. I will show you why. And what is important is these 2 methods. In WAM, so wire arc additive manufacturing, we need to control the process in order to have the same properties of the produced objects. Because this is important because they can be used, for example, in vehicles or in aerospace or in other areas where the safety is important, for example. So yes, this is the main topic here. And also you would like to minimize the defects. So you want to reduce the number of, for example, porosity which can occur inside, or we would like to have the same dimensions. So this is also important to have the highly controlled process in order to reduce these problems. And also, of course, we need to have the same parts produced in the same way every time, so their reproducibility is very important. In the other method, so gas arc metal welding, we also have similar problems and similar aims. So we want to have the same quality every time. And yes, we want to have a good penetration of the weld seam. We want to join two parts with high accuracy, with the same profile, for example. So this is important to have good control of the process. We also want to reduce the defects. So to reduce the time which is needed for repairing this welding. And also heat control is very important here because during welding you can melt also the material which is joined. So yes, this should be also controlled and avoided. So there are also many factors which can influence the welding. So here we have only some of them which are the most common and important, but of course there are more of them. So first of all, when we are welding in a factory, we are using the same machines for a very long time. So after some time there is some wear of, for example, torch or even the robot. So it may be less precise or maybe not good enough to produce good results. And also the characteristic of the wire and other materials which we are using is very important here and have very high influence. And we have to speed up a bit because we are about 10 minutes now. Okay, so everything is very important. There are many factors which can influence the weld seam. So it's very important to have some method for monitoring. And in two projects which we have, we are focused on optical monitoring. And in this optical monitoring, we have also a lot of different problems, like, for example, the arc visibility. Here, I told you that these PMC and CMT processes are very important because in the CMT, we have arc not visible for the whole time, so we can capture frames during these breaks. So this is quite easy to capture images, but in the PMC process, we have always arc on. So this can produce some very high contrast in the images. So yes, this is very problematic. And WAM, we produced a method using size camera, which can capture images which are like here can capture very high exposure time and exposure from the wire. So we have less contrast than with other cameras, for example. And also we developed deep learning method. So first we worked with watershed method, with watershed algorithm, but yes, this was just the initial method. And later we developed deep learning method, where we can just, like here, find where is the weld pool, so this melted part of the wire which is put on the material. And we find out that there is some correlation between the weld size, weld parameters like height or width, and the current. So we can, observing how the weld pool looks like, we can also know what the current is used, and if there are some differences or we want to change this size, for example, we can also reduce or make higher voltage and current on the machine to produce the arc. In gas metal welding, we have Fronius ArcView 2 camera, which is capable of capturing images in HDR mode. I will say more about this in the next slide. And here, with CMT process is quite easy because we have this break between arc visible, so we can capture images without very high contrast. So this is quite easy, but with PMC process, we have very high contrast. Like here, in the upper image, we have image with very short exposure time. So there is only one point where is the plasma visible, but nothing more. If we extend the exposure time, so make it longer, we can see much more, but of course this area which is melted is also very bright and almost impossible to capture. So we managed to use the HDR mode of the camera, and in this mode we are able to capture much more. We can also have some delay to capture images during this lower arc and lower current. So yes, this is our current work. We are working now on the setup of the camera in this project and on making the experiments with the HDR mode. And as I said at the beginning, we are working in two projects. First one is FIT-AM, so the full name is Towards First Time Right WAM. And this project is founded by Austrian Research Promotion Agency, so FFG in short. And this project will finish in the February next year, so this is quite mature. We have this deep learning method already done, and we are working on the control part still. We have some cooperators in this project, like LKR, so some laboratories which are strictly connected to AIT, but we also have SBI, RHP technology, or SPEC surface nanoanalysis, which are also the partners. In other project, Metafacturing, this project is much bigger because it's from European Horizon project and program, and this project will be finished at the end of the next year, so still a lot of work is needed to be done. And we are working on this deep learning method in this area, and also this method and this project is just to provide some solutions for the factories in order to reduce the cost, reduce the scrap, and also to have more science production. Yes, we have many partners from different countries, mostly from this German side. So we have, for example, Fronius, we have Risk. So these are located here. We have LTH Casting from Slovenia, this is a factory for casting. We have Benteler company from Germany, so this is a welding use case. We have universities like Ghent University or KU Leuven. We have also Phil as a cooperator, so there are many partners, and yes, I think that I have to be finished now, so I have to make it a bit shorter. So our future work is mostly needed for the Metafacturing project, because in FIT-AM we are quite mature with our solution. So there we need to make experiments, relearn and retrain the network in order to have better results. Yes, and we will be working more on the setup still in next days. So yes, this is the information that these two projects are funded by FFG and by European Union. And I would like to thank you for your attention, and I'm waiting for the questions.
Thank you, Christian. So, hi from my side. Let's jump right in. Here's a brief agenda. It will be quite an overview. So first I will say a couple of words about myself, then jump into scene understanding, reliability in this context and why we need it, then a couple of use cases such as how to identify completely unknown objects, and then how to estimate depth in challenging conditions, and then reliability in the context of sparse 3D reconstruction. So myself, as Christian said, I did my PhD at TUM in Munich in computer vision. I'm originally from Italy, as you might hear from my accent, and I previously worked at BMW and Airbus around Munich. In TUM, I'm mainly advising PhD students, such as Christian, and I also work towards acquiring new research projects and collaborations with industry, so if you're interested, please reach out. As for the startup, we founded it last year, and we create 3D renderings from smartphone images of products and items, and I'll show you some examples later. So scene understanding comprises a set of tasks that are, let's say, about perceiving the environment from visual inputs. You see here examples of object detection, so placing a bounding box around an object of interest, or we can do that also on point clouds, and the tasks vary from the object level, image level, or even pixel level annotations and predictions, such as segmentation or depth estimation. The problem here is that most state-of-the-art works focus on easy cases and are not really reliable in this sense. Here on the bottom left, you see an example of some, let's say, unusual objects like these boxes that were completely ignored in this prediction simply because the model wasn't trained for that. Above, you see an example of a car with the door open, and this was also misclassified because the shape was different than the usual car with closed doors. Here you see a dynamic vehicle that is estimated wrongly in terms of its depth, and so on. So, but what is reliability here? If you look at these examples on the right, let's say the usual ideal case is at the top, just a standard residential area with good weather, but we want the system, any vision system, to be reliable and perform consistently, not just in these ideal settings, but also in the other cases where we have varying conditions, familiar and unfamiliar environments, different times of the day and weather, dynamic elements, and also some sensor artifacts. In terms of input variations, these could even be generated artificially. As you can see at the top, this noise pattern has been added to the image, and now this panda is misclassified. Or at the bottom left, these few black and white patches added to the stop sign make it be perceived as a speed limit, which is quite concerning. So we want to address all of these issues with a reliable system. Yeah, let's say my PhD was exactly about that. So I worked on various topics such as making the outputs consistent to one another, estimating the uncertainty of each prediction to perform better in unseen scenarios. Here, augmenting the data with these adversarially generated samples, again to perform better in unseen scenarios. Here we were able to detect completely unknown objects and separate them by instance. Here we were estimating depth of dynamic objects with the help of radar. And here we could improve the depth estimation at night and with rain. So in this talk I will give you a bit more details into these two works from last year at ICCV. So unseen unknown objects, why? Well, if you look at these few samples from the COCO dataset, the real world is extremely diverse, and it's hard to condense it into any dataset. So unknown objects will be everywhere and present in many situations, even just on this table. So conversely, unlike previous works that would only rely on certain priors to identify these unknown objects, we were really interested in performing this task and then segmenting everything, including these unknown objects, without having any information about them. And so introduced this new task. And we proposed this method to address it, where we have, let's say, three main parts to deal with these unknowns compared to a standard segmentation pipeline. And that is estimating the uncertainty here at the top over each pixel, then produce some embeddings, pixel level embeddings that are instance aware, and then separating these via clustering into the latent space. So we look at those pixels that are highly uncertain and then separate their embeddings into individual objects. Here you can see some examples. some predictions. So we could even separate these two bears or the frisbees without ever seeing any bear or frisbee or having any information about them. Here you will see you can see other other results and other results with diverse objects, and some are big like these dogs at the top, or very small like this this baseball ball. Okay, so moving to this monocular depth estimation task, again we have a set of easy and predictable cases like the good weather on the left or in the middle, but the problem is that these methods are not reliable when the time, let's say it's nighttime or there is rain, simply because the assumptions on which they learn are not holding anymore. And that is because of these reflections and flares, lack of texture in the dark, and even just reflections in on the ground because of the wet surface. So our goal here was to enable these same methods to deliver reliable predictions in any conditions. And for that we proposed this method where, again, we have three key parts. We transformed the easy images, like the daytime with good weather images, into adverse conditions such as night or rain at the top here. Then we guide this depth model, that is the one being trained, with a signal that is coming from the easy samples only. So from the left here, where we have this depth model previously trained, which can only perform well in good conditions. So alternatively, we feed to this model either a difficult sample from the top or the original sample here, but still guide the loss and the training and the learning from a reliable prediction here. Eventually we are left with a common latent representation for all of these conditions, where we can then at inference time feed any condition to the same model and get reliable outputs. You can see example predictions here, where here you see a self-supervised method on which we applied ours here, and you can see the improvement is significant, especially at night, where the baseline has no clue about what's in the image. We could even identify these two trees that are actually they are visible in this depth point cloud here. That is the ground truth. Okay, for 3D reconstruction, this task is about, from a set of images, reconstructing and understanding the geometry of the scene, both to create a 3D rendering of it or to create novel views. And the challenge here is that with the few available views, this task is quite problematic, and the outputs are not as reliable as you can see here. So in this context, we propose this method, which takes a already trained method and generates images in between the existing ones to improve the coverage. So we exploit its own novel view synthesis to generate novel views, and then we discard the uncertain parts within these generated views and use these as augmentations for training a new model. And with this simple paradigm, we could significantly improve the outputs. As you can see, we started from here where everything is quite confused and inconsistent, and reach something like this, starting from the same 30 views of this counter scene. Here you see down here the corresponding depth estimation, which is more consistent on the ground, despite these two looking kind of similar. Okay, lastly, I will say a couple of words about what we do at the startup. So, as anticipated earlier, we generate these 3D renderings for products. You can see an example here of this shoe. And we do that from just smartphone images. we make it simple and automatic, and we can deliver something like this, but interactive on the browser in just half an hour. And yeah, so if you're interested in making your products in 3D or any research collaborations, please reach out. Thank you for your attention, and let me know if you have questions.
So good morning from my side. Thank you for the introduction. What I'm going to present today is related to a European research project that dealt with the draping of carbon fiber parts. I will later show what this is about. Before I can step into the vision-specific topics, I need to say a few words about the background in which all this is taking place, because that's important for the understanding of why we are doing certain things in our vision sensors. We are talking about carbon fiber composite parts. These are usually high-end parts made for applications, for example, in aerospace, where you try to reduce the weight of parts while achieving the required mechanical performance. These parts are usually designed to the limit, according to the certain safety margins that you require. But the challenge is, if you design parts to the limit, then you need to make sure that they are also manufactured as designed. And this increases the need for quality control when you're manufacturing high-end carbon fiber parts. The manufacturing process for carbon fiber parts basically consists of taking the carbon fiber fabric, cutting it into pieces, draping it into a mold where the single pieces of carbon fabric are placed in a 3D mold. Then it becomes the preform, which is then fixated so that the stack of materials remains as it is. Then it goes into an oven for infusion and curing, and then you end up with the more or less finished part. Some trimming operations are usually required. So that's the, I would say, standard process that you need for carbon fiber parts manufacturing. And visual inspection is relevant in actually most of these steps of the production process. So the defects that we are typically looking for are foreign objects that are on the parts that shouldn't be there, so-called fuzzballs, which are accumulations of carbon fiber that shouldn't be there, errors in the stitching process, like as you can see down here, for example, or distortions in the fabric, as you can see here. So these are the things that are to be detected. And quality in these parts, as I said, is important. But in terms of visual inspection, carbon fiber is somehow the nightmare of any machine vision guy, because it's black and shiny. So if you try to inspect these surfaces, you've always got areas that are underexposed, areas that are overexposed, and that's very, very difficult to achieve high quality images. And I would say it's next to impossible if you just use a single light configuration, especially if the surface is not flat but in some way curved. And to address this problem, we thought about using different light configurations, creating multimodal images, and then jointly analyzing these images in order to improve the quality of the data that you get from the images. And this works basically as it's shown here. You've got carbon fiber surface, you've got a sensor that integrates the illumination and the camera, and then you acquire a set of raw images. As you can see here from this set, sometimes these raw images look quite ugly, with overexposed areas, underexposed areas. But then you combine these images using a physical reflection model of carbon fiber parts, or carbon fibers in particular. And from using these reflection models, you can then calculate feature images. And these feature images, for example, include in-plane fiber orientation. So in this case, that's the colorful image. It shows the fiber orientation color-coded, where color corresponds to a certain direction. But what you can also extract from these images is, for example, a diffuse image component, which shows areas that have high diffuse reflectivity. You can extract areas with specular reflectivity, and a range of other image modalities as well. And the actual power of these feature images is in the fact that they correspond to physical quantities. So you exactly know what these images show, and you can easily determine whether a certain type of defect will show up in a certain image modality or not. And here I've assembled a few examples of typical defects and images that we have acquired. In the top left you see standard carbon fiber fabric with no defects. In the left image the fiber direction is color coded. The blue one below, that's an image showing various gaps, larger gaps between the single tows of the material, or to the right a larger gap or actually a missing tow in the fabric, or up here fuzz balls, which is just an accumulation of carbon fiber. And all of these pictures basically show that it's very easy to generate high contrast between the background and the actual defect, which then makes it easy to segment the defects, classify them, assess their size, and make quality decisions. Now, how is this actually implemented in sensors? We've developed a sensor which is used on the one hand for manual operation. It's got a field of view of 5 by 5 centimeters. It can be placed manually on the part. An image can be taken, and then you receive certain information about the defect, such as its size or other characteristic properties. The same sensor can also be used for automated scanning, which we do very often, as is shown in the background here, in combination with robots. That's when it's about to scan a 3D freeform surface for parts inspection, especially for the finished parts. Other variants of the sensor include sensors for the inspection of large-scale flat fabric. So this sensor is made up of a modular structure which can be actually extended to any length. Typical lengths go up to 2.5 meters, which is a typical range of fabric or size of fabric when it's manufactured. The principle is exactly the same, but it definitely needs a flat surface to work. And a third variant of the sensor, and this is what I will talk about in the remaining presentation, is a small version of the sensor, which has a field of view of about 2.5 by 2.5 millimeters. And the idea of this sensor is that it is integrated into robotic draping systems. To the right you see a larger robot with a pretty large gripper to handle carbon fiber fabric, and the sensor is integrated into this gripper to measure fiber orientation and perform in-process quality control. Draping means the placing of the material, of the flat carbon fiber fabric, on a 3D mold. And this can range from very small parts, as you can see on the left, which are typically draped manually, up to very, very large ones where you need robots to handle large patches of material. The image on the right, for example, shows the rear pressure bulkhead of an A380 Airbus. And in order to do this robotic draping, you need to have a robotic work cell. In the framework of the project, we are particularly looking at human-robot collaboration. So there is a human in the work cell collaborating with the robot, jointly, for example, jointly transporting the carbon fiber fabric from the table to the mold, or doing the fine draping process when there are high curvature elements in the parts that the robot cannot drape. And to the right you see a practical implementation of such a robotic work cell as we implemented it in the project in an automotive company. The heart of this robotic work cell is the gripper that's handling the material, and this gripper consists of a number, in this case up to 24 grasping units, which use suction heads to pick up the material. And each of these suction units can be individually adjusted so that once it's picked up the flat material, the single suction heads can be extended to somehow pre-shape the fabric to fit to the mold in which it's finally placed. Originally we started using suction units for the material handling. Later on we switched to needle grippers because these are more suitable for handling of the fragile material. And in order to give you an idea of what the draping process looks like, I'll just want to show a video. How can I turn this off?
You can exit.
Okay, here we are, perfect. Then let's do that real quick. So it's just 90 seconds. These are experiments that we made at the automotive company Dallara in Italy. They are manufacturing parts for high-end automotive racing cars. That's the robot with the gripper. Here you can see how it's picking up the material. In that case, it's pre-preg carbon fiber material with a protective foil on top. And then in the next step, it moves this material over to the mold, which you can see in the background. The brown foil on top is removed at that stage. This shows an example of a collaborative transport where the human and the robot are jointly transporting a larger patch of material, robot giving a few instructions on how the transport needs to take place and where it's going. And then the material is placed in the mold, the suction heads extend, they retract except a few ones that need to stay in place to keep the ply in the right position on the mold. Then we perform an initial quality check with the sensors that I'll talk about in a minute. And afterwards the manual draping takes place, which is just simulated here. And then you can have some final inspection where you acquire fiber orientations on the part to check whether the parts are as designed and whether there are any defects on the part. Now I'd like to say a few words about the sensors. The sensors are comparably small. They are integrated into the gripper, and each of these sensors, in this case we used 3 in the gripper, is placed at a strategic location where we expect certain fiber orientation to change or where it's important for quality control. And the sensors are also used for detecting the ply edges because the plies might move when it's picked up or when it's placed, and this allows the robot to make some, let's say, last-minute position corrections if you find any of these. This shows some experimental results and how the sensors are actually working in the process for in-process monitoring. This is the gripper, and in the center you see the sensor. These small suction heads are holding the material, and then they somehow stretch or place the material on this mold, and the sensor in the center is monitoring how the fiber orientation is changing over time. And there are actually 3 steps in this process. The first one is the fabric during pickup. And in this case, here you can see fiber orientation or fiber orientation histogram. These are angles from -90 to +90, and the blue area shows how many fibers are going in that direction. And you can see 2 very distinct pink peaks at 0 degree and at 90 degrees. And then when the single suction heads extend and pre-shape, you can see that on the one hand that the angle or the distance between these 2 peaks is increasing, which means the material basically stays in the same position, but there is some shearing taking place between the warp and weft, and the angle between these 2 fiber orientations is increasing. And then as the material is placed, you can see that these peaks change again, which is due to the fact that the carbon fiber fabric then adapts to the 3D mold. And in this case, the distance between these 2 peaks is basically decreasing, so the shearing angle between the warp and weft of the fabric is changing again and getting smaller. We've checked the accuracy of the sensor, and under ideal conditions, we found that it's somewhere in the range of 0.15 degrees, which is quite okay and sufficient for many applications. Ideal conditions in that case means it's dry carbon fiber fabric placed on a flat table in a laboratory environment. In reality, if it's a 3D part and you've got, for example, binder on the material, which changes the appearance a bit, then it's around ½ degree that you can achieve. So these are the results that we've achieved so far with our sensors. And just about the main conclusions that we've had during these developments. On the one hand, this multimodal image analysis is a somewhat powerful tool for dealing with materials that have complicated reflection properties. You can acquire physical quantities that allow you to make a very robust segmentation and detection of defects. The typical defects that you find along the production process of carbon fiber parts can be detected with that kind of technology, and in a particular process in robotic draping, it allows the monitoring of fiber orientation and adapting the process if needed. As all of this has been part of a European project, I need to mention that we are not alone in this project. There are a number of partners involved in addition to Profactor who provided use cases, various technologies that have been integrated into this collaborative work cell. Yeah, so that's the things that I could tell about Drapeout, and I'll be open for any questions. Thank you.
Hello. Yes, so my name is Alexander Eckert, and I want to give that overview over the sensor-based sorting technology. I was working in that field before for several years, and I saw that here on the fair a lot is about vision, but in the sensor-based sorting there are a lot of other sensors which are needed to fulfill the needs of the sorting tasks, and I want to give an overview over those sensors and what the needs are for the future. First at all, not everybody knows about sorting technology in recycling, so I want to show you what's actually needed, which components are needed to sort some waste which is collected previously. So in general, we have an in-feed. Sorry. We have an in-feed for the material. We have a camera. We have a lightning. This is all probably common to other applications shown here on the fair. But additionally, for the sorting, you want to split the material stream into 2 or more parts. So we need additionally a valve to blow away some parts, that in the end we have an output fraction number 1 and output fraction number 2. And for sure the sensors are replaceable, but I will come later to various types of sensors. So the overall content of the presentation is that I show the functional principle a little bit more in detail, which I showed before. I will show some cameras and sensor techniques, and I will give examples of where the sorting is used, in which types of material streams, and I will give examples in which depths the material streams are separated. And in the end, I will go over to what's coming next in sensor-based sorting technology. So first at all, how it works. Again, this is the same setup which I showed before, also with some visualization and some numbers. So we have the in-feed in number 1. This is needed to accelerate the material and transport it to the sensor where it's shown. Then we have the lightning source, we have the camera to capture the data, we have the computer to compute the algorithms to separate the pieces, to calculate which material it is, and to make the decision if it's going to be shooted by pneumatic valves or if it's pathing by. This is how such valves, for example, look like, and this is a row of valves. And in the end, at that position is where the sorting is happening. So the material is blown to box number B, or it's just passing by. And in this special application, which is shown here, is a shoot version. So the material speed in the position of the camera and in the position of the valves are around about 1 to 2 meters in velocity. At next, 2 different options are there to speed up the material and bring it in front of the sensor. It's on the left side a belt version, which is also commonly shown here on the fair, where the material is transported by a belt and the sensor is looking on the belt to identify the objects, or on the right side the shoot option, which was shown before already. there are different benefits for one or the other solution, but in general both are common in recycling industry. And so I want to go over to the sensors which are used. Here are some examples. First of all, the XRF sensor is capable of detecting the elements of a material, what is falling beside or in front of the sensor. The resolution is not that high of XRF sensors because the technology is point technology and every single pixel is very expensive. But you have the benefit that you can see the element. You need for the lightning an X-ray tube, and you have the sensors to detect the X-ray fluorescence radiation of the material. Then another type of sensor is the XRT sensor. Another type of sensor is the XRT sensor. The XRT sensor is used to identifying the different densities of materials, but if you have a combination of two different types of sensors, you also can identify materials based on the elements, and therefore it's widely used, for example, in ore sorting. Then another type of sensors is the near-infrared sensor. Those are also partly shown here on the fair, and especially in the range of 1 to 1900 nanometers, you can see a lot of differences in which is used for ore sorting, plastic sorting, and so on. And not that common type is the lip sensor. Lip sensor is based off a source which is a sensor which is focused to a specific really narrow point. There you create a plasma on the surface of the material, and with the spectrometer you can get the signal and also are able to calculate the amount of specific elements in the source which you are analyzing. Here's an overview over all the different sensors. You can see that all the sensors have different advantages and disadvantages. In general, you can say that the VIS or the UV inspection is the most cheapest and therefore the mostly used. But you have the other sensors, as I showed before, which are needed for specific applications, and therefore they are also used. So probably the common idea is that recycling, you do not need that advanced sensors, but the opposite is the case. We have so much to recycle, and there's so much value in the recycling material, especially when you have a purer and purer fraction, that even really expensive sensors are commonly used in various sorting applications all around in the first world. Mostly there's the money to sort in that cases, while in other parts of the world it's manually sorted. You can see, for example, that especially the XRT and the lip sensor and the XRF sensor are the most expensive, and to give you a feeling for how much the sorting machine costs, equipped with those sensors, it's between 500,000 and 1 million euros for just one single machine. So where it's used for, at first I want to show the example of glass sorting. When you think about the collection of glass in the glass boxes, you do not have only glass inside, but you also have metals, you have plastics, you have other material which shouldn't belong to the glass sorting, and everything has to be sorted out to get some pure fractions in the end. Some material that has to be removed definitely is the ceramics. They make problems later on in the recycling process, you're using WIS sensors, UV sensors, XRF sensors, and near sensors for those applications. The purity which has to be achieved in the glass sorting is really high in the end. You need more than 99.8% of accuracy in the last stage of the sorting process. Also a problem is LED glass, which has to be removed, and those machines are not isolated as one machine, but it's a cascade of machines, and usually more than 20 machines are in one sorting plant, where the input is a mixed fraction and the output is shown here in the next slide. So the output is then the 3 or more different color fractions, which, as I showed before, has a purity of more than 99.8%. To give you an example for the metal sorting, the benefit of metal sorting is that metal has a high value, so there you can invest also more in the sorting technology. Therefore, in metal sorting, sorting technologies like XRF, XRT, and LIPS are used additionally to the VIS sorting. You have the heavy metals, which have the highest value you want to sort out. Is the copper, zinc, gold, silver. But you also want to separate the light metals like aluminum or magnesium, for example. Stainless steel, you could also sort the stainless steel into subfraction of stainless steel. And V, so the E-waste is also coming together with the metal fractions and has a high value. You can also sort by shape, like this example on the right, for example, to sort out the coins of the metal fraction. Then another example is the plastic sorting. On the left side you can see the plastic, how it's collected, so before be shredded. Afterwards material is shredded and then sorted into the subfractions shown also in the row below. For the sorting of the plastics, you use a combination also of different sensors. Could be 3D, could be WIS, could be near-infrared, but also some specialties like mid-infrared or Raman, or again XRT or XRF, depending on the application. The purity which has to be achieved depends highly on where the material is going. So if you want to reuse it again, it needs a high purity, above 99%. If it's just going to reduce the amount of chlorine, for example, to give it to the incineration, then the purity doesn't have to be that high. Here's an example how such a sorter could look like. So this is a belt application. So you have to speed up the material on a belt. You're looking from with the sensors from above, and at the end of the belt there's the valve raw, and the decision is made to shoot the material into fraction A or fraction B. Some more applications I want to show, which are not that widely used, but there are some special applications, for example for wood, to separate wood into engineering wood, paper into subfractions like cardboard or high quality paper or newspaper. Then the municipal waste, which is a mixture of everything in the beginning and then goes into the subfractions, but also textiles, where we as the Research Institute AIT submitted a proposal to dig deeper into textile sorting in the last round of calls this autumn. The other sorting applications are also ore sorting, so not only recycling, but in the beginning, before the material is created, diamond sorting or industrial minerals. Therefore, you can use basically a variety of all different kinds of sensors, and it shows also in how much throughput you can achieve with different kinds of applications. For example, in the ore sorting, you can sort 100 tons per hour per meter of sorting width. What's next in the sorting process? On sensor side, it's going to be cheaper, more precise, and with high resolutions, as always. Then it's more common that niches are filled with some particular new sorting sensors which haven't been used before because they had been too expensive, for example, or they had been too scientific and not usable for the industry. They have to be really robust for sorting. The sorting machines, they are heading for new tasks, also using AI, like always in RGB sorting, but also AI based on all the other data streams we get from the other sensors. For the plans, they get be more automated as before, so always we had some hand sorting until now, but this hand sorting is going to be replaced in future by robots. The different sorting machines will be interconnected. On the sorting goals, especially for Europe, it's interesting because we do not have that much resources, so we want to close the loop, and therefore it's our interest in Europe to sort even more with more quality and to head for closed loops and to recycle material streams that can't be recycled until now. Here's one last example for the AI sorting, which is growing and growing really fast as everything is growing with AI. It's just using, in that particular case, the WIS, but you also can combine different sensors to get even more information and to build cheaper solutions where you earlier used high expensive sensors for different applications. Here's the list of the sources I have, and I want to thank you for your participation.
Thank you very much, and thank you for giving us the opportunity to present our work. So Quest AI is a startup. We've been funded 3 years ago, and both me and the co-founder and several people in the team come from a background in research. So we've been working on European project in different institutes, and in 2021, together with Riccardo, we decided to create a company in order to shift our knowledge in algorithm design, mainly in deep learning and in AI, in like application which could be used in the industry in order to bring innovative products and services to mainly machine builders and system integrators. So briefly, I want to tell you a little bit what we do before we focus on the presentation, which is going to be about the use of event-based camera. We have within our competencies basically this way. Okay, thank you. We have within our like portfolio of application basically the main building blocks of a quality control application for computer vision, mainly based on deep learning, and so we handle tasks such as object detection, OCR, data matrix. Mainly we do anomaly detection recently and the bin picking. So these are the main functionality that you can find when you want to face basically a computer vision problem using deep learning. So these are typically based on standard frames or videos, sequences of videos, and however, there are situations in which the camera, standard camera, may have a limitation, or they may be processes in which you may be interested in analyzing different type of dynamics. Maybe because the speed of the process is very high, and you don't have the possibility to store all the images as you would do in a slow motion video. Or maybe there be situation in which the scene is very contrasty, or the light conditions are not uniform over the frame, and either you need special illuminators. I'm thinking, for example, about application in welding, or you may need to have different type of approaches. So since several years we have the possibility to use a new form of sensor, which are called neuromorphic sensors. Such sensors works in a different way compared to standard frame. Instead of capturing the intensity of each pixel, they record basically changes. So we have typically polarity, activation or deactivation of the pixel, and we have let's say a series of points within the frame which are corresponding to the pixel in which there is an activation or a deactivation, as was mentioned. The very important point is that the information is sparse. So when you ask the sensor to return you the recording or what you have, what the information that you want, this comes as in the form of a list of coordinates x and y and a timestamp. So this basically gives us a representation which is sparse, because we only have the information which are relevant. Think about high-speed process. Basically, we only have the information about the changes in the image, so we don't have to store a huge amount of data. We don't have to elaborate a huge amount of data. And also we can exploit basically a characteristic of this sensor, which is given by not only the high frequency, we have timestamp at the level of the microsecond I was mentioning, but also we have a very huge dynamic range, which makes this sensor very useful in cases in which we have a low light condition or we have a very high contrast condition. So here there is a very simple example. You see the image on the left is a ping pong ball which is bouncing on the table, and we have like a blur due to the speed, and on the right the same image is captured with a neuromorphic sensor, an event-based camera, and you see that we have a much more sharper image. However, when you wanted to process this data, you need to use different type of algorithms, because if you just accumulate the events and you would use standard computer vision techniques, for example, based on let's say convolutional neural networks, then you're not really exploiting the sparsity of the data, because you are going back to a representation which is still a frame, and so you're not really able to process this frame at very high speed if, for example, you wanted to do let's say online control of your data. So there is a lot of interest in designing new approaches, designing new type of algorithm to elaborate this data. And then there is an interest, and this is the direction that we are pursuing at the moment, of how do you combine information coming from one sensor, frame-based sensor, and an event-based sensor. Because, for example, there are situations in which you really wanted to take advantage of both type of features. If, for example, an object is not moving, then the event will not return any data. And so you may not know that there is an object unless the object moves. And also the features, well, of course there are different sensors, but always you do not have the type of feature for surfaces, for let's say shades and colors, which gives you let's say input which is relevant for certain type of algorithm. For example, if you want to do anomaly detection or other type of surface, you have more like features which are at the level of edges typically. Okay, here there should be a video. So this is just to give an idea, the same scene captured by both an event-based camera in a real setting and not an industrial one, if it is loads, okay. And the scene on the left is very dark because of the need to capture the movement. Of course, you have to have an exposure which is very limited, and so clearly you may have issues in presence of a low light condition. While on the right you see that it is very clear when the object is moving. You can have a better detection, and in particular you have the possibility to analytics, and for example sport analytics is one of the area where this type of camera have application. Okay, so how do we combine the two things? I mean the two words, event and camera. So we're using two different cameras, one event, one based. Here in the picture you see like a combination of the two, and a solution which is based on a stereo setting. So there are procedures that allows you to calibrate the two cameras so that you have an alignment between the feature, which is very important when you want to combine the information between the two type of representation. And once you do the calibration, then you can really have a correspondence between the two type of feature, spatial correspondence. Clearly you have a different time, different say frame rate in the case of the camera with the frame, and you have a different time dynamics in the case of the events. They typically work at different orders of magnitude, and so what you can do is that you can design algorithm which at a lower let's say frequency they access the information from the frame, and with a higher frequency they access the information coming from the event. And this can be done in many different ways. For example, you can use the frame in order to reset the detection of an object in the scene, or you may use you can use the frame exactly to reset the initial position of an object, or you may use it to let's say identify new objects which are appearing in the scene, and then when you do the tracking at high speed you can move to the events. And by realigning space and time by as I said, the stereo calibration, and also clearly a triggering time, you can align the two sequences and be able to extract information about the two. So the type of application of interest for us, as I was mentioning, are high-speed tracking, that with this camera can really move to another order of performance due to the timestamp, which are very, very precise, and also anomaly detection. I'm thinking, for example, about an application in manufacturing where you may have a tool in a milling process, and the distribution of the chips can tell you something about the process itself, and usually this correlates with the possible damages for the tool, or in the worst case, damages to the piece that you are working on. So if you have access to high-speed videos of this type of event, you will see that typically there is an anomalous behavior in the formation of the chips, which correlates with the possible failure of the process itself. So related to the stereo calibration is needed because depending on the distance, the alignment is different. So here I have some examples. So there may be settings in which the distance of the object is fixed, maybe in an industrial setting, and so once you calibrate, you don't have to change anymore, and you have an alignment which is fixed. But typically what happens is that if the object moves, then we need to realign using the information of the distance of the object itself. So here on the left, you see that the alignment is done in such a way that we have a correspondence of the feature of the ball with respect and the stick with respect to the frame and the events. Apologize, maybe it's not loading fully the video. Let me see. Okay. While here on the right, we have an alignment which is connected to the ball, because these objects have different distance from the sensor, and so the alignment clearly has to be done. So this can be done in many different ways. Either you know what you track, what you want to let's say align, and you use the information from a depth of a map of depth that you may estimate from the two camera, or you may use an external sensor. These are used so these recording are done using a real sensor which gives us the depth, and we know the object of interest, and we calculate this depth, and we have a mapping between the alignment in order to choose what we want to track and what we wanted to align. Okay, let me move to the next slide. Here there is some more interesting application. So here we are tracking the bubbles of aquarium. You know, the oxygen that the bubbles are inside the aquarium. These typically are very high speed, they're very small bubbles, and at 200 frames per second you see that between one frame and another there is a gap. Some bubbles do not move because they're attached to the wall of the aquarium, and some other moves, and these are, for example, the one that move. And we see that there is a gap here, and also some of them are not very sharp, they're not frozen completely, while the same video is being recorded with the event-based camera, and we have a smooth movement of the object, which allows us to have a precise tracking. Just to give you an idea, this is a video at 200 frames per second. Here we have a visualization period which is basically 25 times more frequent in the representation that you see. So that's why we have the nice small movement. Okay, another thing that you can do is to estimate features from the movement of the object. So in this case here we are showing exactly the video. We are identifying different objects within the scene, and we are computing distances which are very precise, instantaneous distances, instantaneous velocity of the bubbles, and here there is an histogram of such velocities, and these are computed directly from the events. So there is the possibility basically to extract certain features directly working on a sparse representation, which makes this calculation much faster, and then you do not only use deep learning technique, but you also use standard computer vision techniques on sparse representation. And this is an area, is basically one of the approaches which allows to have a computation which are very fast and possibly real time. Okay, so what are we doing now? So some of the videos that I show you have been captured by simply combining two cameras, two USB camera in this case. However, there is the possibility to combine all these objects in a unique object, and this is what we're doing, working in the direction of a prototype based on the fact that these sensors are available. The sensor for event-based, in particular the one that we use, which are the Prophecy one, have been integrated in MIPI boards by Framos, and so by combining this Framos with a Jetson, we have the possibility to design basically a smart camera, if you want, an edge device which has all the computational capabilities to treat at the same time the frames and the events. Clearly, it is very interesting to push as much as possible the computation closer to the sensor, and so such technologies have been also integrated with FPGA, with the possibility to do some pre-processing of the events or some extraction of features which are then of relevance for the computation, and this allows to, by using FPGA, to be even faster in the computation of like extraction of this feature, especially on the spatial representation. Okay, so this concludes my talk. Here I want to show one last video which we took this morning, and it is based on one of the prototypes that we have brought, so if you're interested you can come to see. And here you can see that we are aligning the features of the frame and the events in an environment which is not easy, because there are many lights, there are like a lot of noise, and by using information about the distance, the lines allow you to obtain the two things. Okay, thank you very much. This concludes my presentation, and I'm very happy to answer any question you may have.